Welcome to my report of Lab 3, where we look at a star's motion around a black hole. In this lab, we were asked to generate a computer model for a star's orbit around a black hole, and use the data generated by the model to calculate the mass of the black hole, the velocity and momentum of the star, the directional momentum of the star, and the net force of the black hole on the star. So the first thing we do within our computer model is to input the system properties provided to us by the question. The first of which is the star's mass, and the second of which is the delta T used within the calculations. We're told that the star's mass is 2 times 10 to the 30 kilograms, and we know that the delta T is 1 day, which is equal to 24 times 60 squared seconds. So next we calculate the direction of the momentum, which is done by taking the initial momentum and dividing it by its magnitude. And we then calculate the derivative of the magnitude of momentum, where we take the difference in the magnitudes of momentum and divide by a sufficiently small delta T. To calculate that in the parallel direction, we times our derivative by the direction of momentum. So as we established earlier, the rate of change in momentum is equal to the net force, and this is true for the directional components too. We also know that the directional components sum to the total rate of change in momentum, and we can use these facts to calculate the rate of change of momentum in the perpendicular direction. And then we also know that that is equal to F net in the perpendicular direction. We're also going to be calculating the mass of the black hole, and to do so we're going to use the equation displayed here. We know all of the components of this equation apart from the mass of the black hole. So at the bottom of the screen you can see the code rearranged to calculate the mass of the black hole. Here I also want to talk about the potential for error in the calculation of mass of the black hole, and specifically look at the force used, because the force is determined by the rate of change of momentum, which is dependent on the delta T. And if you were to use a delta T smaller than a day, you would create more data points to generate your values from, which would lead you to a more accurate number for your mass of the black hole. And this is the output of the simulation. This image shows the star orbiting the black hole. The magenta and cyan arrows show the parallel and perpendicular forces, respectively, and the orange arrow shows the net force. So we can see here that the mass of the black hole came out to about 8.37 times 10 to the 33 kilograms. And we can also verify that the two directional components of the net force, when applied together, result in a net force of 7.57 times 10 to the 28 newtons. So lastly, we're going to look at some final questions. In this question, we're asked to discuss the difference between the net force and the rate of change in momentum. As far as the numbers are concerned, the rate of change in momentum is the net force, but in terms of what it means, the parallel component of momentum dictates the change in speed of the object, and the perpendicular component of momentum dictates the change in direction. The second question asks us to imagine that the black hole is removed from the simulation, and that another unknown black hole is put in its place. And we're asked that if we'd be able to calculate the mass of the new black hole. The mass of our black hole is calculated with the following values, which are the net force on the star by the black hole, the star's mass, and the distance from the star to the black hole. In the question, it asks us to assume that the movement of the star doesn't change. And if the movement of the star doesn't change, neither do these values, which means we wouldn't be able to tell the difference if a new black hole were to be replaced. Thank you very much for listening.